today we want to talk about intermolecular forces. Intermolecular forces is very closely related to intramolecular forces, which we studied in first trimester. And it's so close it's sometimes hard for students to understand. So let's start with intramolecular. Intramolecular means they're bonds that are inside of the molecule. And we studied that when you have an ionic bond, you have materials that have swapped electrons, and then they become charged. One becomes positive, one becomes negative, and so they attract to each other. And they pull each other together very strongly and create a bond. And so like sodium chloride was an ionic bond. Materials from opposite ends of the periodic table, a metal with a non-metal. Those bonded together and created ionic bonds, okay? That's what held the molecule or compound together. Covalent bonding is when it was two nonmetals, something like oxygen and oxygen, or carbon and dioxide, CO2 and oxygen. So what happens is when they bond, they actually overlap, and they begin to share electrons in an inside orbital, and they covalently bond. So the sharing of electrons is another inside or intramolecular bond called covalent bonding. And metallic atoms, which is a form of covalent bonding, is when atoms get together and they share, and they get their atoms so close together they share all their outer electrons. And so that's the reason why metals will actually hold together. And so it's another type of intramolecular bond. So these bonds are found inside of materials, holding them together in very strong patterns, okay? And the reason why I want to mention those is because these ideas help us to understand the intermolecular forces. So I want to talk about these type of bonds. So the first one is called an ion to ion bond, which is really just an ionic bond. Okay? Well, how are those intermolecular? If you think about sodium chloride, sodium gives away electrons and is positive. Chlorine is negative, it takes on the electron, and they attract, and that is called an ionic bond. But the ions don't just give off an energy field that go in one direction or to one atom. Sodium gives off charges in all directions, and so does the chlorine. And so what they're doing is they're actually reaching out into space. So this sodium actually is attracted because in a crystal there are numerous bonds. This sodium is attracted to a chlorine in another sodium chloride. And this chlorine over here is attracted to another sodium, which were originally bonded. And then that attraction goes to another chlorine, which goes to another sodium, which were originally bonded. And so what happens now, we go up here, we got a chlorine and we got a sodium, and so this bond keeps going over and over and over again, and we call that a crystal lattice. So ionic bonding actually creates other bonding called intermolecular bonding, ion to ion. Okay? So this creates a crystal lattice of energy, and that lattice then pulls all the molecules together. So this extra forces that are reaching out and pulling the other ions in is an increase in bond or intermolecular forces. So it's between the molecules. And so this helps create a lot of solids. And that's the reason why we find a lot of solid materials have ionic bonds inside of them. Okay? So that's one extra intermolecular force that helps create different states of matter. So we are talking about why we find solid, liquids, and gas. I should say solids and liquids. So this is a change in state. Why do we have more dense states of matter? So that's the first and the strongest type of intermolecular bonding. The next one's called dipole-dipole. It's pretty easy to understand when you're working with water. Water has covalent bonds inside of it. Okay? But it's called a polar covalent bond. It is a polar bond, meaning that the hydrogen and oxygen are bonded. They're sharing electrons, but they're not sharing very well. The oxygen has a rating of 3.4 on the electronegativity scale. Hydrogen has a rating of 2.2 on the electronegativity scale. So what that means is this element, the oxygen, is pulling harder on those shared electrons because it really wants a full octet. So these electrons exist more of the time in the oxygen cloud. making the oxygen starting to develop a negative charge because the electrons are there. Well, if the electrons are pulled off the hydrogen, then we see a developing charge of positive on the hydrogens. So then the whole molecule becomes slightly charged on each end, and it call it a polar molecule, or having two opposite ends. The word di means two poles of charge. Well, if you put two molecules that have two poles of charge by each other, they're going to attract. Okay? So the reason why water actually is not a gas is because two water molecules want to be by each other because their polarities pull them together. So here's our one polar molecule, and there's an attraction, and so the water molecules keep pulling, so they pull themselves into a different change of state, and we see them, this extra intermolecular force is caused by their dipole interaction. To prove that to you, I want to do a quick demonstration. If I'm correct, I'm going to come over here, and I have a burette with some water in it, and if I open up the burette, I get a very fine stream of water, okay? And you probably can't see it very well, so I will hold up a darker piece of paper to do that. I'm going to take this balloon, and I'm going to rub it on my hair and create a static charge. If what I said about water being polar is actually true, then the water molecules will churn and rotate so that the opposite charges are attracted. I can get the water to bend towards the balloon. So I rub my hair, creating a negative charge or on the balloon, and I turn the water on, and I hit my fine stream, and we can see the water be impacted by the balloon. You can see the stream of water is being bent away and it's actually getting water on the balloon. I can hear it rattling. So we keep going. My water going better. Oh, I lost my stream. So rub my hair. You can see the bending water. See? And that's because water has a polar nature to it. So that's what's happening in water. So water pulls on itself, and so when water wants to freeze, then what happens is water actually has to rotate to make sure two water molecules don't have the same charge by each other, because that's a repulsion. And so what happens is water then has to create a bigger molecule, or a bigger group I should say, and that bigger group when it's frozen takes up more room. So water expands when it freezes, and it's all because of this dipole-dipole interaction. Okay? So dipole-dipole is a situation where we have a polar molecules, and those polar molecules end up creating a situation, polar molecule, and they like to help create our liquid states of matter. So another intermolecular force can be found because of that situation. Okay? Now the last one is called dispersion, sometimes called linear dispersion, and that happens when you work with extremely large molecules. And what it means is these molecules can be temporarily dipoles, so it's called a temporary dipole. So they are not a material that has a dipole, but they are induced to having a dipole. Well, how does that occur? My best example would be a magnet and a paperclip. I take two paper clips, and we can tell that there is no attraction. But if I attach a magnet to this paperclip, it now actually can become magnetic. So while the paperclip is near the magnet, it is magnetized. But when we take away the magnet, we find that the paperclip is no longer magnetic, so it is a temporary situation, and we can't get them to attract. But when I have the magnet close by, now of course the paperclip is now magnetic. So the paperclip is not magnetic, but with it, a magnet around it, it becomes magnetic. That is dispersion idea. Okay? So we take a polar molecule like water. It has opposite charges. It's a dipole. We take a material that has a large set of atoms creating it, and those large atoms, what they can do is those clouds are extremely large, they can distort, and so then the electrons begin to be pulled towards the positive part of the dipole, and then the nucleus back here begins to get a little exposed because the electrons are over here more of the time, So now this molecule becomes polar, but only while this dipole is near it. So that can happen with extremely large materials that have large atoms in them. And so what temporarily, they can be pulled into a more dense state of matter. But when these dipoles have been removed, they go back to being probably a gas or whatever. So what it is, it's called dispersion. It's a temporary dipole situation, and it occurs in creating different states of matter as well. Okay? So these are the three intermolecular forces. The strongest one is ion to ion. The second strongest is dipole. We find that more for liquids. This one's more for solids. And then dispersion helps to create why some things also can be found in a liquid that really should be a gas, is because this extra force that does occur. Okay? So that's our discussion on intermolecular forces.